Good morning, everyone. Welcome to part one of this short course on causal inference, which is conducted as part of the AA for Ops seminar series. Thanks for being here. It's my great pleasure to introduce Sanjay Shakkottai. Sanjay is a professor in ECE as well as Cockrell Family Chair in Engineering at UT Austin. And Sanjay is my academic big brother. He got his Ph.D. in ECE from University of Illinois, Urbana-Champaign. His research interests are broadly in resource allocation, statistical learning, and networks, with applications in wireless networks and online platforms. Sanjay received many awards, which include the NSF CAREER Award. He's elected as IEEE Fellow, and more recently, he won the Bennett Prize from IEEE Communication Society. He's currently editor-in-chief of IEEE ACM Transactions on networking. So today is part one, and we'll have this a 5-part short course, 10 to 12 every day of this week. Various locations, see the ad for more details. But I also want to point out that the lecture notes that Sanjay is using, the handwritten lecture notes, is already posted. You can find the link either in the announcement or from the AA for Ops website. So Sanjay, the floor is yours.
Thank you. Thank you very much, Siva. It's a great pleasure, and thank you for the invitation, and thanks to AA for Ops for hosting me. So a little bit of background. So what, as Siva said, I'm interested in networks and machine learning, and specifically representation learning. So the way I got interested in causality is that it provides one way to think about invariant representations. But before we get to that, I'll only get to these kinds of statistical issues, finite sample issues, representations, and so on the last day. The first 3 or 4 days is going to be sort of more traditional causal inference, because I thought it's worthwhile to sort of have a background in this. So none of the works which I'm going to be talking about I've had anything to do with. I'm just compiling the material from various things. The last day, I'll talk about some of my own research. Okay. All right. So with this, this is first caveat. The second is that I'm going to talk about causal inference, but my goal is sort of for machine learning. And so it's going to be a sort of statistical view. I'm going to avoid any philosophy. So there's a lot of philosophy associated with causality. I am not going to talk about any of that. I'm not going to claim that this is the model of causality. This is a useful model of causality. That's all. That's the viewpoint. And I don't want to get into the flame wars or the politics of whether this is the right model or not. I'm presenting something which makes a lot of sense, which is useful for things which many people care about in the learning world. Okay. So these are the caveats. Now, with that, the material which I'm going to be talking about are primarily taken from these 2 books. The first being Elements of Causal Inference by Peters and others, 2017, the great book. I'm going to call it text from now on. Whenever you see reference text, that's really what I do. The second is the book by Pearl, Causality, 2009 book, which I call Causality book. So in terms of presentation style, much of the material I'm going to talk about is borrowed from the Elements of Causal Inference, the first book. But I want to emphasize that most of the original papers and the material can be attributed to Pearl and his colleagues, at least the things which I'm going to talk about. I am just using book A because it's easier. If you are sort of coming from a probability or machine learning background, the language is somewhat easier, at least for me to follow. So I'm using A, though really B should be the quote-unquote primary source. Okay. All right. So these are the caveats. And with that, let's get going. So in the first, today I'm going to break it up into 2 pieces with about a 15-minute to 20-minute break in between. The first part, I don't want to do anything. I don't want to start building formal models or any such thing. Let's just talk about motivation. Okay. And Siva, please slow me down if I tend to zoom. As you know, I sometimes have that bad habit. Let's talk about correlation versus causation. Okay. So the simplest toy example I can think of is rain and wetness. So consider the following thought experiment. I stand outside for an hour every day. Okay. I record the following pairs of Bernoulli random variables, meaning 0 or 1. That's all I'm recording. Rain, comma, wetness. Every day I get this pair. If it rains and I get wet, it's and I'm wet. So let me restate. It rains and I get wet. So it's an and. I'm not making any causal statement, right? There are a pair of two things which I observe. Okay, it's purely observation. Then it's 1, 1. No rain, no wetness. It is 0, 0. Okay, maybe I should not point to the board, but on the screen. That way on the Zoom as well, people can follow. Okay, so this can take 4 states, 0, 0, 0, 1, 1, 0, and 1, 1, meaning based on whether it rained on that day and whether I got it. So I collected this data set, and let us, for now, consider the population case. What do you mean by population case? I have infinite samples of this pair of Bernoulli random variables. It essentially means I know joint distributions. Meaning, if I model this as a pair of correlated random variables, I have some joint distribution, and I have access to the joint distributions. We'll worry about finite sample issues, learning these models, and these kinds of things on day 4 and day 5. The first 3 days, essentially, I'm going to deal with population case. Okay, which means that when you see a distribution, you have black box access to it. You can query a set of values. You can query 0, 0, and it will give you a probability. That's basically the underlying assumption to it. All right. So you have this pair of random variables. We can ask, are R and W correlated? And that's easy. You can do this by following. You query the following conditional probabilities. So when I say you have joint distributions, I also assume implicitly that you can marginalize it, you can do conditioning, you can find all these kinds of things. You have black box access to all these kinds of distributional information. Yeah. So you can query ask the probability whether rain is 0, and given that wetness is 0, is it equal to the probability that rain is 0 given wetness equal to 1? If this is true, or we can query if wetness equal to 0 given rain equals 0, or wetness equals 0 given rain equals 1, and check whether these things are the same. This will tell us about independence essentially between these two random variables, and we can check the correlation. So that's what I mean by these kinds of questions. These correlation questions are testable from infinite samples. Okay. Now let's move to causality. We would like to find one way to ask the following types of questions. Does me getting wet cause rain to occur? Meaning, does wetness cause rain? Or does rain cause wetness? Right now, we haven't defined what cause still means. But as society, we have some qualitative understanding of cause. So suppose I just put these kinds of questions down. Then how would you go about answering this? Presumably, if our rain and wetness are correlated, they're not independent, then both of these will not be equal to each other. The first equation will lead in inequality, the second will too. So using this, you cannot really say which way the direction of implications. Okay. Potentially, you will need to do more experiments. So let's think about a set of 4 experiments to check, to test for causality. Meaning to test for these 2 statements. Statement A is wetness causes rain. Statement B is rain causes wetness. There's a message on chat. I will not be able to follow the chat. Okay. I see a red flip. Okay. So wetness causes rain and rain causes wetness. So these are the 2 statements I'd like to test. The previous data, again, I'm trying to introduce some language which we'll build up later. We'll call observational data, meaning you observe this data from your base experiment. It's already given to you. Instead, we may need to do something else, which we'll call interventions. So let's do the following 4 experiments. Experiment 1. For 1 year, or actually forget about 1 year, every day, because I'm now dealing with infinite samples, ignore the 1 year. I have infinite samples. Each day, I stand outside with an umbrella, whatever the weather may be, and record again the pair, rain, wetness. That's experiment 1. Experiment 2. Every day I stand outside and get a bucket of water poured on me. Okay, that's experiment 2. Experiment 3. Using a cloud seeder, rain is forced to occur every day. Okay. Experiment 4. There's a giant fan and all clouds are blown out of the sky. These are 4 interventions we are talking about. Of course, these are cartoon interventions, but makes the point of changing one of these variables. Okay. When I talk about these 4 experiments, there are some implicit assumptions going on. That putting the giant fan blowing the clouds out of the sky is not somehow changing my state of, it's not affecting me, it's only affecting the rain. Okay. So even when I state these, there are buried assumptions, which I'm not going to talk about explicitly, but we should keep in mind. Because finally, we are talking about a modeling framework. And so any modeling framework has all these assumptions. Right? Here I'm explicitly pointing out the kinds of assumptions that are being made. But now, summary is so far, I've gotten 4 new data sets. So using this, suppose we can compute, we'll compute the following 2. So remember, when I say I have a data set, I have infinite samples, meaning I have distribution knowledge. What does it mean? From model 1, I have infinite samples of R, W. And so I have the joint distribution of rain and W, but not under the original probability model. I've changed the model. Okay, I've changed the joint distribution between rain and wetness by standing outside with an umbrella. Okay, because wetness in this example, my wetness state is always 0. Okay, so the joint distribution is a different joint. The generator model has changed. That's really what I mean by the joint distribution has changed. In the original experiment, rain wetness, there is some model nature chose to have a joint distribution between rain and wetness. Okay, this is a new model. Okay, this is yet another model. So that's what really we are talking about. 5 different probability models of the pair rain, wetness. Let me make sure this is an important point. Actually, this is one of the things which we'll see all the way through for several days. That we are no longer reasoning about one distribution. We are dealing with a collection of some related distributions. Okay? That's the first takeaway we have at this point. Good. So now I have these 5 different distributions, right? Including the original one. Suppose we can compute the following. Under model 1, we call what is model 1? Model 1 is the umbrella. Okay. Look at the probability rain equals 1 given wetness equals 0. This is under model 1. We can compute this. And then we can go to model 2 and ask, what is the probability rain equals 1 given wetness equals 1? Remember, in model 2, there's a bucket of water poured on me every day. It's a different model. Okay. There's a model. So no longer are we asking a question about one model. We're asking, there are 5 different universes, and I'm going to ask questions between 2 separate universes. Model 1, where there's an umbrella, and model 2, where there's a bucket of water. And I'm asking whether the probability rain equals 1 given wetness equals 0 is the same as probability rain equals 1 given wetness equals 1. Going back, you see that this is very different from the correlation question. In correlation question, we were asking this question with the same probability model, the observational data. We are no longer dealing with one model, we are dealing with 2 different models. If these are equal, then we will say that wetness does not influence or cause rain. Okay, meaning, now, so the graphical model of this is have a variable for wetness, have a variable for rain. We'll put an arrow which also indicates a direction of causation. Okay? If these 2 are equal, then this edge we will delete. Okay, there could be other edges as well. Let's go back to the other 2 experiments. Now we want to check whether rain causes wetness. Yes.
So, equality that had been true for all universes?
This equality only no. So I'll answer your question. So his question for people who didn't hear is, should it be true, this equality true for all universes? Answer is no. I'll come to 3 and 4 and then we will see what it means. When we have two variables, W and R, there could be many relations. So this could be one picture. This could be another picture. A third picture could be this. So we need to resolve among all these three different things. Okay, which is what, and implicitly, I'm going to deal only with acyclic graphs. Okay, so I'm not even going to go to cycles. So in anything I'm going to talk about. So there are only these three pictures which I want to deal with. Yeah.
When you say three pictures, these are all causal pictures. You could have correlations.
Correlations,
but you
correlations simply I'm going to call as this. I'm not going to put an arrow.
Oh.
This is my model for correlation. This is the model for causation, or this, or this. Okay. And furthermore, you will see in a few minutes that there could be correlations without an edge between these two. Because there could be a third and a fourth thing which could have some relation, which could show correlations. So I want to separate between so correlations is not even drawn in this picture. Okay. So all I'm trying to right now talk about is relationship, explicit relationship between pairs of variables. Coming back, yes.
Why do you condition the proof of always under limits? Because things like that P1 or R equals 1 equals,
Good. This question is, why am I putting condition W equal to 0, W equals 1 when that's already encoded in 1? Okay. The answer, because 1 basically is wet, the universe is always wet. Okay. Just to keep things consistent with this classical probability notation. I could have written this exactly like this, and that would be valid. In fact, this is not a notation we are going to use later. Okay, I'm going to go to a notation of doing and do calculus. This is a qualitative introduction, so I'm using some notation here to make it look like classical probability theory.
So it's the same probability, but because
yes, because in this universe, every sample wetness equals 0. So whether you put this or not is immaterial when I talk about model 1. Okay, so it is not wrong to put it, but it is not necessary. Okay. But at least but writing it this way makes it clear what the correlation question is asking versus what the causation question is asking. That's why I wanted to write it this way. Okay, good. And
your method for this causation exists or not, you use some sort of knowledge of the system, right?
I am assuming there are only two variables in the system. I can do interventions in the system. Okay, meaning I can take the model and change the I have a mechanism by which I can change the generator model of data and collect infinite samples. Is what I'm assuming right now. Again, that doesn't mean this will, later on we'll change all this. Okay, I want to tell 3 stories in the first hour. I want to tell 3. So is it okay now?
Yeah.
Okay. I want to tell 3 stories right now, and then we will come back to the questions you ask and sort of formally build everything. Okay. This is very informal for the first hour. But coming to your question, which yeah. So now suppose I want to understand whether rain causes wetness. So this is a different question. Okay. And for this question, what will I do? I need to look at models 3 and 4. In model 3, remember, I was forcing rain using a cloud seeder. And model 4, I was forcing no rain using a giant fan. Okay. Now let's check again in this world. So in model 3, rain is always 1. In model 4, rain is always 0. And in these 2 models, let me check the probability that wetness equals 1 and probability wetness equals 1. Yeah. Let's ask whether these are the same or not. If these differ, then I'm going to conclude that rain has a causal effect on wetness. Okay. So hopefully you get a sense of this notion of causality which we are dealing with here. Okay. It is summary at this point is that correlations are tested using observational data. Causation, at least the definition of causation we are using here, which is Pearlian causation. This is Pearl's is that it's tested using interventional data, that is data generated by actively modifying in a variable, and therefore having a new generative model of the data, and then computing distributions or conditional distributions. Yeah. Is example 1 clear? Okay, good.
So what's 3 and 4 ever probability? Like probability 3, it's like you can get weight given in.
Yeah. So in 3, what is happening? It rains every day. So presumably I will get wet every day. In model 4, or maybe let's say that the world is more complicated than just rain. There are other things also happening. Okay. But nevertheless, I potentially will get wet most of the time. In model 4, presumably, because I may still get wet because of maybe somebody has a hose or something like that. But presumably, I get wet much less frequently. And because these are different, I can say that rain has a causal effect on them. Yeah.
From this example, can we say that we can make causal statements only when we have intervention?
Excellent. That is the first takeaway. That's the first limited takeaway. It's not clear whether you can resample the observational data to create fake interventional data. We'll go to that direction soon. But right now, all we have said is that causal statements are causality is really a statement about interventional data and not about observational data right now. Yes. In general, yes, it will scale exponentially in the alphabet size. Okay. All this is the most general. Can you do much better than this? Potentially, yes, but let's go down. Right now, I just want to set what we mean by causation for the next 5 days. This is what we mean. That's all. Yes.
So we have a mathematical theory of probability, omega FP joint expression.
Yes.
No, you're going beyond that. You're going outside.
I am not going outside the mathematical theory of probability. Good. I am basically having a collection of omega FPs. That is all. Actually, a little bit more than that, but we'll get to structural causal models only tomorrow. It's what we have, at least at this point, is not one omega FP, but multiple omega FPs. Or one omega, one F, and many P's. Okay, really is what we have. Many probability measures on that space, each measure generating a different pair of elements.
That's going to make this formal at some point, or can it be made?
Yes, it can all be made. When we build the models, it will become much more clear what we mean. So that's tomorrow. Today, the first hour is very informal, so that it's clear where I'm just trying to position the rest of the series. That's all. Okay. So, and now I'll give you a look ahead into the language we are going to use, and this will come back and address your question. So in model 1, remember that we had an umbrella, and so wetness was always 0. So the way we are going to write this probability, this is just a traditional conditional probability with a generative model of 1. The way we are going to write this is through something called do. Okay, we'll say that probability, when we put do W equal to 0, means we have done an active intervention, and therefore we have changed the generative model of the data to set the wetness variable equal to 0. We are doing something. Okay, this is the Perlian framework of causality. By the way, there are other frameworks as well, which I'm not going to talk about. For example, potential outcomes and so on. I'm just sticking to one sort of model all the way through. Okay. So we do. So this basically says this is an intervention, and we are intervening on this variable. And in that world, we are looking at rain equals 1, given wetness equals 0. And sometimes I'll be sloppy and not even write this. So these are equivalent. Okay, whether we write this or not in this world is equal. One more important thing to notice. You can ask, hey, for do equal to 0, can I just look at the data, the original observational data? Forget about doing any intervention. Let me look at the original observational data. Remember, there's nothing fancy going on. And just look at those samples when wetness equal to 0. And then from that, just look at that data set and compute things. That's very different because that's just a traditional conditional probability. Okay, so doing is not conditional. That is another important takeaway. In the what does doing really mean? It means you look at the original data set on every day, whether wetness was 0 or not, force wetness equal to 0 and regenerate samples. So it's a different generative model, and therefore data is being regenerated. That's really what do means. Do is not conditional. Okay. Under some circumstances, doing is the same as conditioning. We will use that later. And this allows you to do an interesting calculation. But for now, doing and conditioning are completely different operations. Yes.
So when you say do and then you study the restaurant, does that mean that and variables we set that value, or is there a way to enhance that and say?
We will, right now it is set. Can you do not as a deterministic but random? Yes, we can do all those kinds of things. But right now, for example one, I wanted the simplest example to illustrate the things we want to talk about. So this is that's all we are at right now. Okay. All right, good. The way we sort of graphically show this is the following. So through these experiments, suppose we have concluded that this is equal and this is not equal. Suppose after these 4 experiments, we concluded this. Then the way we would draw this is this picture. Rain is causing that. This is a graphical summary of what we did. Now, really what we are doing, I said that there are a bunch of random variables, right? Which are being generated according to various intervention models. Really what is going on is underneath the original model, there is some generative model for this data, meaning the following. Presumably, there are N1 and N2, which are independent Bernoulli random variables. So now I'm going to talk about a generative model, which will give that omega p, all that stuff. So there's N1 and N2, which are independent Bernoulli random variables with different probability, meaning there are 2 separate coin tosses. Okay, 0, 1. N1 is 0 with probability 1 minus P1 and 1 with probability P1, and N2 with P2. This notation, this is setting. So I'm going to set rain equal to N1. That's what this is saying. Okay. So, and then I'm going to set wetness is the mass of rain, comma N2. So what does this mean? Let's go through this. So this is generating an acyclic thing if you look at the way the variables are written. First, a pair N1 and N2 are generated. Suppose N1 was 0 and N2 was 1. N1 is 0, so rain is 0. And then wetness is max of rain and that other independent random variable. So wetness could still be 1. So this is an example where you could still get wet independent of rain. But if you look at from these equations, if you didn't put this dot equal to, you would say that there's correlation between these things, and you could always rewrite things the other way around. But this is essentially giving you a causal model. This gives you a direction of how things are influencing. And the way you test this is to change these equations. So what did we do in those generative models? We changed this. When I said that I'm holding an umbrella, I changed this model to get rid of this and just set this equal to 0. Okay, that's a new model, which will give you a new joint distribution between rain and wetness. So really what is going on are multiple joint distribution. But if you look under the hood, what is happening is that we have some language to specify the underlying ground truth model. And then we are changing one or more. Any intervention is a change in one or more of these equations, and then regenerating data with that for testing directions. Yes.
Confused. So when you're doing interventions, you're only changing R and W, but then the N1 and N2 are not touched.
It's a new sample. So it's a new world. N1 and N2 are regenerated. So you could also couple N1 and N2. This will lead to something called counterfactuals. And I'm not going to talk about it in these 5 days. I'm only going to talk about observational and intervention. Third level is counterfactual. When you ask, am I dealing with 5 different probability models? You could also define a coupling across those 5 different probability models. And that is something I don't want to talk about, but that's sort of what you're getting to with N1 and N2. Let us say that what I will do for simplicity right now is I will then take a new N1 tilde and N2 tilde, change these variable equations somewhere and redo this. Okay, that's what I'm going to talk about. But there's a whole theory of counterfactuals, and I don't want to get to that. Okay, I'm going to talk only about observational and intervention. That's it.
So what's the difference between this sign of equality, like double dot equals to sign, and the normal equality?
If a normal equal to sign basically means, suppose there's a plus, I could do algebra on it and take rain is equal to W minus N2 or something like that. And then I can test for correlations. It's one model. This is essentially saying, how is my joint distribution generated? This will generate, these set of equations will generate an acyclic directed graph from which we can draw samples and get a joint distribution.
So here we cannot take terms.
We will, but when you're doing an intervention, it basically means we are changing equations on this. Okay. So our 4 interventions was, this was set to 0 and regenerate data. This was set to 1, regenerate this data. This was set to 0 and regenerate the data. And this was set to 1 and regenerate the data. Okay. So these are 4 different new equations I've defined. But each one you are generated sample. That was the intervention.
So the interventions are not just about like forcing N1, N2 to be 0. It's changing the actual form.
Exactly. We are changing the functional relation. An intervention really is changing the functional relations in the underlying generated model. Okay. That's why I brought this at this point. And these are called the structural causal model. So tomorrow again, we'll start with this formality. Okay. Good. That was story number 1. This is still a toy example. Second question is, why is this useful? Okay. Question number 1. So I want to talk about this famous kidney stone dataset experiment. Okay, this is Simpsons Paradox. In the text, it is these examples, and this is originally from Chadwick's paper in 1986. So this is the dataset. Let's spend a little bit of time looking through this. It's from 700 patients. There were 2 treatments possible for people with kidney stones. Treatment A is open surgery. So make a large slit in your abdomen and then presumably get into the kidney, remove the stone, stitch everything up. Treatment B is a much smaller surgery. It's a small puncture surgery called precutaneous nephrolithotomy. Okay, I guess it's a keyhole surgery, what we call. Okay, much smaller surgery. And right now, let's look at some data of success with these things. Overall success in treatment A, there are 350 patients who got treatment A and 273 the treatment was successful. Oh, sorry. So 78% is the success rate of treatment A. Treatment B, 289 out of 350 recovered. So the treatment B has a success rate of 83%. So clearly from this data, treatment B is preferred over treatment A. Okay. There's an issue of what are my confidence intervals and all. Just from these means, you can't say it. But let's say that those things are all okay. And I'm going to avoid those issues. I'm just going to look at the raw numbers and say, at least from this data, treatment B seems to be better than and significantly better than treatment A. It's a nice big gap. Now let's look at patients with small stones. Now I'm going to go back into the data and look at the stone sizes. Okay. And based on some diameter, I'll say it's a small stone or a big stone. Okay, the kidney stone. So if it's a small stone, patients with small stones, 87 of them had small stones, and treatment A, 81 or 87 succeeded, which was 93%. Treatment B for small stone, 234 out of 270 succeeded, which is 87%. So here, it's clear that treatment A is better than treatment B, which is exactly the opposite trend of overall success. That's fine, because we have other categories as well. Let's move to the third category. Third category, with large stones, treatment A, 192 out of 263 succeeded, which is 73%. Treatment B, 55 out of 80 succeeded, which is 69%. So the summary at this point is the following. if you have a small stone, treatment A is better. If you have a large stone, treatment B is better. If you have treatment A is better. But if you have a stone, either large or small, and you don't know what size it is, then treatment B is better. This is Simpsons Paradox. Okay, if you haven't seen this before, you can take a minute to digest this. Okay. Right? So this is bizarre. It doesn't make any sense that for the state of this variable, if you know it, gives you improvement of this. But if you don't know the state, the other one is better. Okay. It's a meaningless statement we know from everything we understand about the world. Why is this? What could explain this? Well, here's a possible story. The doctors know the size of the stones. So for easy cases, this is a cheaper surgery, treatment B. So you prescribe that to patients. For hard cases, you prescribe treatment A. So treatment A is only used in cases where the recovery rates are lower, presumably. It's a harder situation. Okay. And so now this could potentially make sense. Right? Yeah, we'll get to this in a second, but I'm just trying to give you a qualitative reasoning why such paradoxes might occur. In fact, you can take any data set, partition it into parts, and so in each part, the trend line is the opposite from the overall trend line. It's always possible. So you can take this, this basically says that you should only partition data if it's meaningful to do so and to look at each partition. Okay, that's a separate story. I'm not going to go down the probability story of it. I want to talk about causality. So where does causality come in here? This is called Simpsons Paradox, and a causal perspective on this. So you can see Pearl's book argues that there is no paradox. So I just sort of pasted a little bit from one of Pearl's paper. So using sort of the language, we can resolve these kinds of things. Okay? If you're interested, you can sort of dig more into this paper often. So the intuition is essentially the following. Now let's draw a graph having these three variables. And let's say that we know the true underlying causal graph. Okay? So meaning there's the size of the stone, which is 0 or 1. That's going to affect the treatment T. The doctor decides to use 0 or 1. 0 is the cheap treatment. 0 is the expensive treatment A. 1 is the cheap treatment B. And recovery or success is again 0 or 1. The treatment did not succeed or succeed. Is the model clear? There are these three variables. And what is happening is Z is a confounder. So I'm introducing new language now. If the relation between treatment and recovery is being influenced by Z because it affects both the choice of the treatment and their recovery. So an incorrect reading such as if you do not know the size of the treatment, size of the stone, treatment B is preferred. But this is clearly wrong. And we will need to really answer the following to check whether treatment really affects recovery. We will need to really do the following interventions and check. So somebody says that there's a Z, this is what you're given with. You have these three variables, treatment and recovery. This is the data. And I want to check whether this edge exists. That's what we care about. What do? We need a way to delete this edge, okay, between Z and T, and then get data from this distribution alone. Suppose I could do such an intervention. What does this mean? This is a randomized trial. That's what is, I'm just giving you, right? As a doctor, I will prescribe A or B independent of the state of whether it's a large or big. That's really what deleting this edge means. This language. Is that clear? Okay. So I need to do such an intervention. Then with this new model, we'll call it C prime, we can check the following. In this model, we can look at probability that recovery is 1 given treatment equal to 0, and probability recovery is 1 given treatment equal to 1. Suppose in this model, this deleted model, these things are not equal. Then we can say that treatment has an effect on. Yes.
So when you say treatment has an effect on recovery, this is not, you're not just saying that if you take treatment, it will help you. You're saying that the choice of treatment.
Yes, the choice of it. Because I could say even, I could put a third one basically null. I could make a 3, 2, 0, A is keyhole, 0 is keyhole, J is large puncture surgery, B is keyhole surgery, C, do nothing. So really we need to check with that third option as well. Okay.
But here you're.
I'm using this qualitatively, right? Yeah. So I want to really, this is what I care about, whether treatment has an effect on recovery. And this is the intervention that's needed. And that's what, now in this language, that is basically what a randomized trial is. Okay.
So suppose there is that arrow. Now, what is that saying? That is saying that these two treatments have different effectiveness on recovery.
This arrow, if it's there, says
not that arrow, the T to R arrow.
T to R, yes.
So by deleting that edge, let's say now we have established that there is an arrow between T and R.
Yes.
Then we're saying that
the choice of the treatment impacts the recovery. Right. That's what we want. This is really what we
care about which treatment is better.
Yes.
That is, the picture is not telling that, but
the picture is saying the structure, the probabilities will. And we'll get to that in a second, called average causal effect. That's how much will it improve. Yes.
In this example, the two conditional probabilities that they are comparing are under the same model, under the same.
This new model, yes.
So both of these are from the same new model.
Correct.
But in the first example,
I needed 4 because, yeah, I'm not saying how many models of interventions we need or any such thing. So this goes back to our question: how many intervention models are needed? In the worst case is exponential. Here, there's just one interventional model that is sufficient to answer this question.
So my question is that how do we decide whether we want to be looking across different fields?
We will. Very good question. We'll start addressing this soon. Right now, we are just talking about 1, 2. We potentially will need to look across very different types of do's, and let's punt all that to later for this week. I just want to make sure that for this first session, I just want to make sure the story is clear. I have one more story to talk about, which I think is important as well.
So how do you calculate this probability?
I don't know right now. Yeah, I have infinite samples. So how do I calculate this? This basically means I have a randomized trial. I run this trial for several years, where doctors are forced to prescribe A or B using a coin toss and not using knowledge and study this. Is this ethical? That's a different question. Again, I don't want, there's a lot of other issues about what interventions mean and whether you can do this and so on. I'm going to avoid any such question. I'm just going to talk about models and what this is. Yeah.
Okay. So in this example, let's say we deleted that edge. There are 3 possibilities. So treatment A always better than treatment B in both cases. Other way around. And the third possibility is that for small stones, treatment A is better, and for large stones, treatment B is better. Does the picture differentiate?
This picture doesn't say anything about the probabilities, but I'm going to not answer your question, but wait for a few minutes and we'll come back to your question. Okay. All right now, I just want to tie it back to the language. This probability, by the way, this example we are going to come to multiple times to speak. So if I don't get to your answer today, we will answer it maybe tomorrow. Okay. But it is there. The answer to that is there, but I just don't want to sort of sidetrack there, right? So the C prime model is really a do. What have we done? C prime, do treatment equal to 0. Do you see what this do basically means now? I am forcing this variable treatment to be equal to 0 or 1, irrespective of the state of anything else that may influence. So hopefully this connects what we did in the first example to what we are doing here. Deleting this edge. So the new model is we delete this edge and set this to either 0 or 1. And we collect data from each one of this. So really we are doing 2 experiments in one. Okay. That interventional example, I said that randomized trial. Randomized trial is really 2 examples. 2, you can take that data set and break into that part of it where treatment was 0 and that part of it treatment is 1. So it's run as one experiment, but there are 2 separate interventions that are happening there. Okay. So I think that gets back to what you were asking. Okay. But the way we write this is do t equal to 0, do t equal to 1. So one of the main goals in causal calculus is checking or potentially trying to compute these interventional probabilities, but using only observational data. Is this possible? Maybe, maybe not. Okay. So essentially, one of the cornerstones here is what it's not called a total probability theorem, but I think of this as a weird type of total probability theorem. Remember your total probability theorem and probability. Probability of A equal to probability of A given B times P of B plus probability of A given B complement times P complement, right? This is your total probability theorem. But this standard total probability theorem is all with the same P. This data from this, the P's in all the probabilities are from the same generative model. It would be nice if you have a total probability theorem which has probability from one model can be written in terms of expansion with probability with a different model. Okay. It would be nice to have such a total probability theorem. Okay. So it turns out that there is this, but the rules are different. If I done the usual chain rule, okay, suppose there's just one model, P of R given T is P of R given T comma Z times P of Z given T times something. These are my total probability theorem. This is not that. I'm not trying to explain this right now because I'm going to spend a whole lecture on just this. Okay. Right now, I'm just pointing out that if there was a total probability theorem, actually this is called an adjustment. If there's such a total probability theorem that could relate probabilities under one model given in others, then we are in business. Because we could fake interventional, we don't do conditioning, we do something else to take observational data and compute interventional probabilities. Okay. This is going to be one central thing which we are going to discuss over this week. Okay, and coming back to Siva's question, if you do that for this, okay, it turns out for this problem you don't need any new experiment. Okay, for the kidney stone example. Using that table of data, there's a way to compute the interventional probabilities, and you can check the following. Given treatment equal to 0, which is the large thing, the success is 0.832. Given treatment equal to 1, which means doing treatment equal to 0 gives you 0.832, and doing treatment equal to 1, which is the small one, gives you 0.782. And therefore, this is different, and that tells you, quote unquote, the true benefits of treatment A and B. Okay, and this is not using any new data, just using the previous table. There's a way to compute these probabilities. Okay, there is no paradox, and this difference between on treatment 0 minus the probability of treatment 1 on recovery is called the average causal effect. So this is an answer to your question. Only I didn't tell you how I computed this. Okay, but it is doable, and we will actually. I want to derive those equations and then come back and compute it. This will be tomorrow or day after.
What's the difference between C and C dash?
C is this universe, where the doctor presumably is using the size of the stone to make a decision on which treatment that the doctor wants to offer. In C dash, the doctor does not use the information on the size of the stone to make a decision on whether treatment is good. That's the difference between these units. Yes. Yes, and you're removing the incoming edges and setting this. That's one way to do it. There are several ways to do, and tomorrow we'll talk about it. But what you're talked about is one way to do this. It's already 50 minutes. I have one more example to do. So let's take a, we are going slow. We'll see where at least today I want to make sure that I keep on pace. I'll continue with example 3 because it'll take me at least 20 minutes to talk through example 3. We'll do it after a 20-minute break. So essentially these things will be run as sessions of 50 minutes, 2 every day with a 20-minute break. That's the plan for the whole thing. Okay. Thanks. Let me take a pause now and then we'll get back. Okay, let's get started. Thank you for coming back. So I want to get to the third example. And third, I want to motivate CI testing, conditional independence testing, okay, which is actually very important for all of causality. We basically, in the first 2 examples, we saw that really testing for causality is testing for correlations. I was using the word correlations. Really, I meant independence. They're very different things. But so it's except for Gaussian models, they're very different things. So it's testing for independence or condition independence in interventional models. But intervention really means observations in a new model. So it's always everything comes down to conditional independence testing under some observational model. Okay. So CI testing is going to be important all across, and we'll spend actually all of Friday doing CI testing. So that's one of also things I'm interested in as a research direction, efficient CI testers. I'll talk about some of those kinds of things later. But the third example is the following. I can view the second question, a special case of the second question we talked about, as the following. Suppose somebody told you there's this Z, the latent, okay, which affects both X and Y. And you know that the direction arrow is potentially from X2. So you are essentially given that the nature is from one of two different graphs, this one or this one. Okay. That's a special subcase of the questions we talked about in 2. If I know that and ask, can I determine from the data which one it is? Then this is another answer to Siva's question. Okay. Does the treatment have any effect? Okay. But I've told you everything else about the model. And I've told you there are no other extraneous variables. There's nothing latent. Everything is observed. So what I mean by nothing latent is there could be a fourth more W variable here, which could affect, which is not even recorded. That's a whole different ball game. We'll worry about that maybe on Thursday. Okay. So, but right now, a special case of asking the same question could be, can you distinguish between these? So this is a hypothesis testing question. This is a null hypothesis. Treatment has no effect. Alternative hypothesis, treatment has effect. This arrow in the story is really, I'm just positing, how will I test for this arrow? Because this arrow could be one, I'm already telling you the arrow, if it exists, is only in that direction. So it's really this question. This is a classical probability question. Are X and Y conditionally independent given Z, or X and Y not conditionally independent given Z? It's not really binary because what not means is not a single hypothesis. Okay. Again, I'm brushing some of those things under the carpet right now. These things are going to become very important because this is really not binary. This is eliminating the null. That's really the kind of question we're looking at. And we'll talk about the statistical issues with this and the hardness of this problem and things like that. Statistical hardness of this problem on Friday. But this problem, H0, are X and Y condition independent given Z. The notation I'm going to use, if I do a double bar with a line, that's independent. This is the standard probability notation. And language you will here in the causal world, this is called controlling for Z. Controlling for Z are X and Y, or adjusting for Z. These are the language. If you read these things, this is really what it means. So I'm also introducing some language here. Okay. So you want to test between these two. And so you can see that without if you know this much, without any additional experiments or interventions, you can learn or not the presence or absence of these edges under lots of assumptions. Because again, there are, as I said, there are lots of finite sample issues with this stuff because it's not a binary question. It is actually, this is a continuum. This is an infinite collection of models. Okay. So now you may ask, hey, if I could just reduce things to CI testing, then why do we need all this language of causality and all this stuff? Because finally, all I have is a CI tester. Okay. So this is my generic formula now. I want to check whether A and X and Y are condition independent or not. Take every other variable, condition on that. Do I CI test between X and Y? It should be done. Okay. And the answer is no. And I'm going to do this in 2 passes. The first, suppose I have all other factors, Z, and some side effect, which is both affected by the treatment and the effect. Okay, this is some other variable. Then my recipe would be to condition of Z comma R because I wouldn't know anything between that and check whether X and Y there's a treatment or there's an effect. It turns out hypothesis test will say there's an edge here even though there isn't. And to make this concrete, so it will lead to a long conclusion. So before I do this calculation, I want to say what the implication of this is. This essentially says that in feature for machine learning, in feature selection, you had extra features. You think put everything into the bucket and fit a model. Actually, things can get worse. Okay, that's what, because you can think of Z and R as features. Okay, putting extra features can actually give you bad models, and we will see. So it's not just a computational issue. There's some other issues as well. This also can lead to wrong conclusions, even qualitatively. We'll talk about Bergson's paradox tomorrow. I want to just spend a little bit of time doing this calculation. Here I just hand waved through. I didn't tell you that the edge occurs or not. So let's do a very elementary calculation, it's an undergraduate probability calculation, but we'll make it clear what is going on. Okay, we are going to take a jointly Gaussian model. There are these three variables: Z confounder, treatment, and effect. Z, X, and Y. Okay, I'm going to posit not a Bernoulli model, a joint Gaussian model. Okay, so Z is an independent Gaussian. So we shouldn't think about a binary treatment and effect. We can now just move to a stylized model. There's a confounder which is a Gaussian. Z is a Gaussian zero mean unit variance. This thing. X is AZ plus N2, it's a linear model. And Y is BZ plus N3. So N1, N2, and N3 are three independent, identically distributed Gaussian, standard Gaussians. Okay. And these are just traditional equations I've just written. Okay, no structural causal model and all that. Just written three. X is written as A times Z plus N1 plus N1. And no, A times Z plus N2. It has, so each one is generating independent noise as well. There's a model. Okay. So let's look at this. Let me fit, using these two, I'll fit something to this. Okay. What do? I solve least squares. So I don't know A and B, right? I have access to this model. Meaning I have the joint distribution between, as I said, I'm in the world where I have joint distribution. So I have the joint distribution X, Y, and Z, so I can compute anything I want, okay, from this ground truth model. So what is the fit I would do between, because the linear model between X, from X and Z to Y? Well, I will solve the least squares problem. I'm in infinite sample setting, so I can just put in expectations. I don't need to look at sample averages, okay? Fit Y, I'll do gamma X minus beta Z, full square, right? This is just standard least LMS, least mean square. So how will I solve this? Usual, right? I'll just take, this is all linear stuff, take the derivative with respect to gamma, take the derivative with respect to beta, solve the pair of linear equations, and see what the fit comes out as. So I'm just writing down the LMS. I know this is boring, simple stuff, but let's just do it. Okay, let's just write down the LMS. I'll take the derivative, write the equations. So if I'll get the standard linear LMS equations, okay, least mean square equations. And so this is all like in undergrad prob in our sophomore year, we teach these students. So there's nothing fancy going on here. Okay, all of these things can be computed from the data because I told you that I have access to the joint distribution between X, Y, and Z. Again, there's no interventions, nothing. There's just one model. This is the model, okay? And I'm just trying to figure out, I'm trying to just do a fit from here to here. That's all I'm trying to do. So yeah, you can compute this. For example, if you want the second moment of X, X square is, it's just A square because the Z is independent of N2 and you can just compute things out. Similarly, you can compute every other thing, stick it in, solve for this. And you do get what you hope will expect, which is beta is B and gamma is 0. What does it mean? It says that this should be beta and this should be 0. So you have learned through least squares the right model to fit these two to this, which is you will get Y hat equal to B times Z hat, your data, plus 0 times X hat. Perfect. There is no true causal effect in this model, and least squares actually determines this correctly. Are you with me so far? Nothing fancy here. Now, let's say this is the model. Okay. So there's confounder, that's your for the store or whatever. There's a treatment, there's an effect. In reality, there is nothing here, 0. But both the treatment and the effect affects a side effect, something else. So there is a D and a E here, and A and B here, but this is a 0. So this is the now ground truth model. So what's formally Z is N1, X is A Z plus N2, Y is BZ plus N3, W is DX plus EY plus N4. That is this model. Let's do regression again. I'm going to regress on these three. I'm going to regress on this. Okay. So what do? I have three variables, gamma, beta, and phi. This is what I'll call gamma, this is beta, and this is phi. Forget about directions, forget about causal, right? I have this bunch of variables, I want to fit Y. And so let me again write for three of them, I need to go through the mess. I can take the derivative of these things, write the linear regression equations, solve them. You can check it. I've written everything in gory detail. I'll not bore you with these minutiae. But if you solve these three equations, ideally, what do we want? We want to get gamma is 0, beta is B, phi is 0. Meaning we want to say that Z hat is B times Y. That's all you want. We want this to be 0 and this to be 0. But that's not what we get. We get that if that was indeed, if this is what we wanted, and I substitute that into the set of equations, we'll see that these equations are not satisfied. What it's giving is adding extra covariates adds spurious dependencies. It's simply because we are putting something here, and even though there's nothing happening here, some correlations is leaking through this way and giving some complicated fit on all three variables to this effect. So this is what I meant by adding extra variables actually gives you the wrong answer. Siva, you look.
Why should we expect 2 zeros? We should expect only one. Right?
No, because really in this model, if I want to find, I should expect this to be 0 at least, right?
That I should expect to be 0.
I don't.
The other two we don't.
Fine,
yeah.
But you will not get anything. You will not get this to be 0 either. In fact, this also should be 0 because there is no arrow this way.
But in this model does not have arrow in it, right? Arrows come from causality. This is causality.
Right. So if you do a fit, you're not going to. Ideally, what you should say is the best fit should be only Z. If I want to find what is
okay, I think I understand what's going on. So the mathematical model you have there is not causality. There's no dot equality and so on. This is just a classic probability.
If I want to find the causal effect, I'd like 0 there. I'm not getting that.
But what least square is saying is that if you give me Z, X, and W, this is my best guess.
Yeah.
And what it's saying is that Y does depend on Z. That's clear.
Yeah.
But if you tell me W, I do have information about Y. So it's trying to estimate that. But W also depends on X. So it's trying to compensate.
Yeah, exactly. It cancels and fit some model. Exactly. That's really what is going on. Absolutely. So adding extra covariates or variables it will give you the best fit, but it will not generalize. But that's not what we are looking for. Our question is not. We are using a fit as a surrogate for something we really want to figure out. Remember, our goal is to figure out whether there's an effect from X to Y. And we are using this fit to try to say, if the coefficient is 0, then the answer is, that's what the example is saying is that this is a wrong way to go about doing things. That's all. Okay. Therefore, the structure of the model is important, and all the causal calculus we need will be important. But going back to the previous thing, we can reduce, if you know the variable and potential structure, you can reduce things to CI testing. In fact, CI testing or conditional independence testing, from now on I'll use CI testing all the time for conditional independence testing, is the sort of workhorse of all sort of causal inference problems. Okay. So right now I'm talking about the forward problem here. Okay, for today and tomorrow I'll talk about the forward problem. What I personally care about is the reverse AI problem. Okay, learning models. So I'm giving you either graph, I want to learn the structure, or given a structure, I want to make inference on something, how many samples and so on. All this uses CI testing as a black box. You'll need to use it for testing various properties. So it's worthwhile to spend time thinking about this basic tool. So these are all the examples I have. So summary so far is reasoning about dependencies in a family of related distributions. So you have to make the interventions. You have to do interventions, which basically use observational data from a new system and reason from there. Sometimes you don't need to go to the interventions. You can fake the interventions by using from just observational data. And yeah, all these things require us to understand sort of conditional independence among observed variables. That, yeah.
So does this mean when you include the effect in your model will do regression, that can
Side effect.
Okay. So if we are considering time series model, meaning that we are regressing on its own path, since there is like a nature order time, does that mean we can actually identify the other effect?
If you are careful, very good. How do you do time series? I wasn't planning to talk about time series at all here. The one way to deal with time series here is actually do unwrapping. So you look at each variable. Look, suppose you have a variable x, but now you can call it xt, xt plus 1, xt plus 2. And then the arrow of time always moves forward. Okay, so you can build a causal model, which is a time unwrapped version of the variables, and then you can start doing infinite on the semi-infinite. Depends whether you are interested in finite time, then it's a finite time model and so on. There are interesting tools for doing things. Off the top of my head, Igramite is the sort of state-of-the-art tool. If you want more information on, but I'm not going to deal with time series at all in this short. Okay. Okay, so now this was so far storytelling. From now on, I'm going to sort of, for the rest of today, I'm going to just start doing the probability theory needed for this. Okay? And then we'll come back to, so today and tomorrow's first lecture will have no causality. It's all about directed graphical models, conditional independence, what does independence mean, all these kinds of things. Just the probability plumbing needed for all this work. Okay? It's just straight, that's it. And so this again from a bunch of sources that what I'm talking about has been taken from. The two texts, of course, Element of Causal Inference and Pearl's book. But beyond that, there are a bunch of other really nice notes which I use. At UW for Stat 535, Intro to Bayesian Network. There's a course at HKUST by Yan Zhang, and also this very nice book called Handbook of Graphical Models. Mostly chapter 1, it's a book by a bunch of chapters. The first chapter by Bilan Rene is what I'm. So all these are the references. I put more detailed references so that you can actually go back to the original sources to go into the details. Okay. Setting. I have x1 through xd, a collection of random variables with some joint distribution across these. I'm going to use a notation of discrete, though almost everything I talk about works with densities. Life is just easier if I write it in discrete, so I will write it in discrete. You want to do continuous? Yes, it works mostly, except here and there. You can go to the books. Notation, a sub I. I'm going to use random variable xi takes value little x. This is bad abuse of notation because I'm using I to denote two completely different things, xi and the value of the random variable I and the value xi. So I should actually have AI comma bi and put bi. I'm just being sloppy here. Okay, but mostly it doesn't cause any trouble for the things I'm doing. But keep this in mind that I is actually indicating two different things here. Okay, so this is really what I should have. This is the kind of notation, but I'm not doing that. Okay. So the chain rule of, so I have a joint distribution x1 through xd, which is just the probability of AI, intersect of AIs. We have the usual chain rule. I can just decompose the intersection probabilities as usual. Notation, independence is this, conditional independence is this. Okay. And all this conditional independence means is that probability of AI intersect AJ given AK just breaks up into products. All very, very basic stuff. I'm just writing it out so that you have the notation consistent, nothing more than that. Okay, the first lemma. So again, from now on, we are just switching tracks. I'm just going to do lemmas proofs for the rest of today. This is a very, it's almost immediate, but it's a very, very useful observation that to test for conditional, if AI and AJ are conditional independent given AK, if and only if you can find a pair of functions, phi ik and phi jk, such as the following is true. The probability of the intersect of AI, AJ, and AK is given by phi ik of xi xk times phi jk of xj xk. If you can find such a pair of functions, then this is an if and only if condition of conditional independence. I don't know whether you've seen the proof of this, so I thought I'll just write the proof of this. It's useful. I hadn't seen. At least in my undergrad class, I don't teach this, so it's worthwhile to just see this. So the forward proof. You're interested in AI intersect AJ intersect AK. So I give forward is I'm assuming I and J are conditional independent given K. So it is nothing but AI given AK times PAJ given AK times PAK. Okay? Which can be rewritten as this is PAI and AK divided by PAK. This is PJ, J and K divided by K times PAK. This cancels. I can write this as square root. I can take this and break it into square roots. And that's what gives me this. So now I've found a function. This is just a function of I and K. This is just a function of J and K. So we have said that the triplet can be, we have shown that this is written in this form. That's one direction. The opposite direction. So suppose I know that there exist these functions such that now I'm assuming this is true. I want to prove this. Okay. So what is I and K, probability of I and K? Well, I know IJ and K can be written this way. So I can just sum over all values of J. I can just marginalize out J to get this. No? Okay. So I sum over all values of J. And if you notice, this does not depend on J. So this pops out of the summation. And so by moving this here, I will call gamma 1 of xk because I've marginalized out J here. Okay. This gamma 1 of xk. Similarly, I can look at J and K and marginalize out I. And so I will get JK and then gamma 2 of xk. Now, note that if I want to check for conditional independence of I and J given K, that's if and only if the following is true. That is probability of AI and AK times probability of AJ and AK divided by PAK is IJ and K. Why? Write this as P of AI given AK times PAK. So that cancels with this. This one is PAJ given AK times PAK. That is just PA. Okay. So it's just two ways of writing this. Just algebra saying that conditional dependence can be written. So now I have expressions for this. I have expressions for this here. To find an expression for AK, I can take this equation, for example, and marginal out J as well. So I can sum over J to get this, which is what we'll do. So denominator, I'll marginalize out J, PAJ and AK. And so this did not depend on K at all. So if I sum over all J, I'll just gamma 1x. I know this algebra, but I'm just going through this so that you see how this proof works. You stick everything in and you will see that you recover that from this example, you will get that this is equal to the product of phi ij and phi jk, which by the starting assumption was equal to the probability of the triplet. So the summary, so this is a very short proof. This basically says that to test for conditional independence, you just need to find a pair of functions, I, K, and JK, such that the product of the intersection of all three can be factorized in this.
Yeah. I can simply think of it as a Markov chain, possibly inhomogeneous. So this I to K, so IKJ is the Markov chain. That's the
yeah.
So I to K.
That's right. That's another way to think of it. Yeah, that's right. That's all. I said this is not deep, but this is very useful for proof. We'll just use this for testing for condition independence. We'll use this lemma all the time. So that's why I'm thinking this. Good. Okay. So we have kept that aside. We have now gotten some way of sort of algebraically testing for condition independence. Now let's come back to tags. So I have a graph. D is a set of vertices. D is a number of edges. Number of vertices is D. I want to represent the collection of random variables as a tag. So each variable represents one of the random variables. Okay. And the DAG encodes a certain factorization, meaning. So if I give you a directed acyclic graph, the joint distribution is factorized in the following way. It says for any variable j, Paj given parents of Aj, it's a directed acyclic graph. Okay, the joint distribution is written as a product of the probabilities of every variable given its parents. That's what the DAG formally encodes. So when I drew those causal graphs, really this is what I'm encoding there. Okay, for example, look at this. This has the so the joint this is a joint distribution between 5 variables x1, x2, x3, x4, and x5. And this DAG encodes the following: that this joint distribution is x1, it has no parents, times probability of x2 given x1, it has only one parent, times probability of x3 given x1 and x4, times px4, times probability of x5 given x2 and x3. So it says, this DAG says that this joint distribution has this following structure. Okay. The high level goal is the following. If I give you this DAG, but I don't give you all these algebraic equations. Okay, I don't actually. So this DAG hides a lot of things. It doesn't tell you what strength of variables are. It doesn't say anything else. It just gives you a structural relation. Okay, the fact there's edges there basically means it's a non-zero thing. That's all it's saying, nothing more. Given this DAG, can we read off conditional independence relations among the random variables? What do I mean by that? Are x2 and x3 conditional independent given x5? Or are x1 and x4 conditional independent given x3? I can ask any question. I can condition on some subset of these nodes and ask for independence among variables elsewhere. Is there a systematic way of reading off conditional independence from the DAG? This is a very useful question you can see for causal inference more broadly, but this is a question which is it's of interest in itself. So that's all I'm going to do for the rest of today and also first hour of tomorrow. Okay. Yeah.
So just to clarify, no interventions, no causality.
There is no. I have just stopped talking about. I'm just talking about classic probability on one distribution. No interventional distributions or any such thing. I'm just taking one distribution, and I said, now I'm taking the joint distribution among these random variables. I'm drawing a directed graphical model which says how these random variables are related, and saying that this is a way of encoding the following property. Okay. Why is this useful to causality? That's for first hour was some high-level statements. We will make all these connections later. But for the next hour, go on faith that this thing will be useful. Right now, it's just math. Okay. All right. So, if a question is, if from this can I read off CI relations? That's a very useful question for various things. And people have studied this for about 100 years. So the history of this problem goes back to 1930s. And there are different ways to reason about it. Again, I'm going to take Pearl's way of reasoning about this through something called deseparation. There are other ways to reason about it, something called moralizing. If you want to read that, are alternate ways, you can go back to this paper. This is from 1990. This is a really nice paper. It's in parallel. It's a different way to reason about for this question from graphs to depict CI properties. This is what I would suggest you look at. So, is it clear what I'm trying to answer? I'm trying to answer these. I'm trying to answer these kinds of questions given this graph picture. The problem is conditional independence is an algebraic property. Really, it's not a graphical property. So can we actually look at graphs and can we infer something about CI? The answer is a qualified yes. And to do that, we are going to introduce a different independence operator. Right now, it has nothing to do with independence. We are calling it an independence operator because of the theorem that's going to follow, showing that this thing implies certain independence. This is called deseparation. Okay, and is the way we are going to denote it is the independence with a G, saying there's a graph associated with it. This is the notation. This is all directed graph. Good. Undirected graphical models is a completely different game. We are dealing with directed graphical models and acyclic. If it cycles, it's again another game. I am not going to. So this is very much directed graph. Undirected, we can talk offline. That's but yeah. I'm only, yeah. All right. So I'm talking about directed because that's when I can talk about parents and children and all this kind of stuff. Okay, good. I'm going to talk about deseparation, and the goal is two-stage. We'll define how to define this operator, this deseparation operator, and we will show something called the global Markov property. Meaning, if x and j are conditionally deseparated given xk, that implies x and j are conditionally independent given xk. So it gives, this is called the global Markov property. So it goes from graphical reasoning to CI reasoning. And we will talk about faithfulness, which goes the other way. So that's basically what we are going to talk about for the next hour. Actually, 20 minutes today and then continue an hour tomorrow. So let me go through deseparation, the definition of deseparation. So this is from Deseparation Without Tears by Pearl, or Pearl's causality book. Language, a path. So consider a collection of random variables, I, K, L, and J. There's a path is an undirected sequence of edges. That's all. I don't care about direct. So when I talk about path, it's always undirected. A collider is the following. Pick a path in your graph. Say, let's say I'm picking this path. So this is the path I'm picking. Okay. Along this path, so I've just redrawn this here, x1, x2, x5, and x3. A collider exists on this path if there is a node on which all edges are incident. Both edges, it's just a path, so just pair of edges. So this is a collider because this is both incident. Okay, that's what is called a collider. Note that a node can be a collider. This node x5 is not a collider. It is a collider only for this path. Let me give you a different example. Let's consider this path. On this path, there are no colliders. Okay, so I'm fixing a path and then talking about properties. So collider is a property associated with that path. This x5 is a collider for this particular path. With me so far? So we say a path is blocked if it has a collider. I'll do this in two passes. The first pass, I'm just going to define it and go back and do one more pass on exactly the same things. Rules for deseparation. I'm going to say that xi and xj are deseparated or graphically independent if every path between xi and xj are blocked. So here, let's talk about this and this. Okay. Are these deseparated? This is one path. Okay. This path is blocked because there's a collider. This is another path. This path is blocked because of this node. There's a collider here. Okay. So I have looked through every possible path in this graph and saw that x1 and x4, every single path is blocked. And therefore, x1 and x4 are deseparated.
Yes. I have a basic question about path. Like a path starts with one node and finishes at some other node.
With no nodes repeating. A path is simply an undirected sequence of traversals with no repeated vertex.
Or, like, what do you mean if a path is blocked? So you have to check two paths.
So I suppose I want to check x1 and x4 and check whether they're graphically independent. Okay. What I will do is first figure out every path between them. So this is one path. This is another path. Okay, let me wait. This is another path. And there are only two paths for this. Because if you look at it, once I get here, I can't come back. Okay, I can't repeat nodes. So between x1 and x4, there are only two paths in this graph. Okay, so now pick path 1. Let's call this path 1. Now check whether there's a collider on this. There is a collider on this. So I'll call this path as blocked. Look at the next path. Check whether there's a collider on this. There's a collider here. So this path is also blocked. And therefore, X1 and X4 are deseparated.
What if there is no path? What if there is X7 sitting somewhere?
It's a directed acyclic graph, single system. There is no path. Okay.
So that is still
That's
graphically
null.
dependent?
They're graphically null. I'm going to only deal with connected graphs. Yeah.
That's why I'm trying to believe that the deseparation would depend on whether XP is observed or not. If XP is observed,
I'll get to all that. I'll get to much more. I want to start. First, let's just talk about independence. So, question. No,
Well, he's saying more than
I'm
that.
saying more than that because this,
X2 to X3, there's no direct path.
this, or X, yeah, X. Let's look at this. There is no directed path here, but they are not deseparated. Okay, so it's not only about directed path, it's about lack of colliders. Okay. We can talk about it in different, it is exactly this. Any other statement may not work. I don't want to even go down that. Okay, there is this is the set of statements that work. There is a completely different set of statements that also work. That's called moralizing graphs. I'm not going to go down that set of statements. Okay. I'm just doing this way of reason. Collider. If there's a collider on a path, that path is blocked. If all paths are blocked between a pair of nodes, then there is. That's my zero authority. Next. Conditioning. I want to now make this definition work with conditioning. Conditioning does two things. Let's look at this graph, X1, X2, X3, X4 with these in this order. So this edge is going this way, this edge is going this way, this edge is going this way. With no conditioning, there are no colliders on this path. So X1 and X4 are not deseparated. You agree? Because there are no colliders on this. There is no node on this where there are both sides incident. So this graph, X1 and X4 are not deseparated. Now let's start conditioning. Conditioning on a non-collider blocks the path. If this is a non-collider, I condition on this, it immediately blocks the path. This is again a non-collider. If I condition on this, it blocks this path. I could condition on both. It still blocks the path. So again, always my discussion is going to be about a path. To check any property between variables, you enumerate through every path and then resolve questions at the path level. Okay. So anything I'm going to talk about is a path level statement. Are you with me so far? Conditioning on a non-collider blocks a path. Conditioning on a collider or any of its descendants unblocks a path. Okay. So let's look at this. X1, X3, X. This is the graph. Look at this path. This path has a collider. So by default, X1 and X5 are blocked if I didn't condition anything. If I condition on this, it unblocks this path. If I condition on this, it again unblocks this path. If I condition on this, it again unblocks this path. If I condition on this, it blocks this path.
This is the definition of blocking.
I'm defining operators. I'm defining collection operator. It looks a little bizarre, but I'll do it in multiple passes to see that actually it makes sense.
You said you only look at a path. So why do you have a separate thing, X6, X7?
Because conditioning on a collider or any of its descendants unblocks a path. When you're conditioning on a node, you need to check on all descendants of colliders. For this path, this is the path I care about. This is the path I care about. But there happens to be a collider in this. So therefore, I need to look at all its descendants. Okay. Why do I need this rule? let's look at this following example. I toss a coin, Bernoulli, 0 or 1. Okay. You toss an independent Bernoulli coin, 0 or 1. We are independent. All you do is exclusive OR are two numbers. Meaning, if I am 0 and you're 0, you're 0. If I am 1 and you're 1, you're 1. And if I'm different, no. If both of us are the same, you're 0. If both of us are different, you're 1. Okay. So, knowing you correlates our states. So, conditioning on a descendant breaks. That's really why. You see. So, let me repeat that statement. Knowing a descendant correlates its parents. Okay. So, conditioning on colliders will correlate parents. A conditioning on a mutual descendant, essentially. That's what this is trying to capture. Let me go through this bunch of rules once more. I am interested in checking whether a pair of nodes are graphically independent given another collection of nodes. This is my goal. So I need some rules to define this. And this is the definition. Path is an undirected sequence of edges. And if I want to test a generic property, these two are conditionally independent given this. What do I do? Well, I'll start with the pair of nodes. I'll enumerate every possible path. There are two paths here. So let's first look at this path. On this path, there is no conditioning happening at all. Okay, so there's a collider. So this path is blocked. Look at this path. On this path, there is a collider, but it has been conditioned. So it's unblocked. Therefore, X1 and X4 are not deseparated condition on X5. Another example. Let me condition on X6 alone. This is one path. There's a problem. This is because it's a descendant. Already it's conditioned on a descendant. So this opens up this path. So they're not deseparated. Okay. So you can see how this reasoning is working. The rules are simple. Color in all the nodes which are conditioned on, and then enumerate every path between the pairs of variables. On each one, just apply the set of rules. If you are conditioned, if it's on that path, if the nodes you've colored in is not a collider, then it's blocking that path. So let me do one more example. Suppose I condition on this and this. Okay, let's see what happens. Look at this path. There's a downstream node of this. I'm looking at this path. X3 is a collider. There's something downstream of it, which is blocked, which is conditioned on. So it opens up this path. But let's look at the other path. Okay, I'm conditioning on this and this. So this is a collider. Condition on this opens up this path. But there is a block node elsewhere. So this path is blocked. So as far as this path is concerned, this conditioning is blocked because of X2. As far as this path is concerned, this unblocks this. So they're not deseparated. But you see, for each path, you need to argue differently. Is it making sense? So this answers your question of what I mean by, I don't want to talk about observer. It is what are you conditioning on, and then reason path by path. This is what deseparation is. Now, a completely defined a graphical. This is a complete set of rules. Okay.
So if a path, you said something blocked the path, something unblocked the path. If a path has both a block and an unblocked, it's considered blocked.
Yes. If there's a block, as long as there's one block on the path is blocked. Good. That is the other rule which is unsaid here. Okay. I'm going to prove it in a minute. No, I'll just do it. I'm right now I'm giving you a set of rules. It's clear why conditioning on a collider unblocks it. Conditioning on this, suppose I condition on these two. Okay. And let's look at this and this. There are only two paths between these two. Both are blocked. Because you can see that any relation between these, if I knew these two values, it's intuitively clear x1 and x2 are condition independent. That's what blocking on a non-collider, condition of non-collider. I'm separating any possible influence that x1 or x5 have are completely conditioned on x2 and x3. There is no more influence. That's what conditioning on a non-collider means. That
So in this example, X1, X4, they are separated condition of X6.
they are not deseparated. Why? Because of